Hello, my name is Ben Moldenhauer, and today I'm presenting my work titled Characterizing Experimental Nonlinear Modal Coupling with 3D Surfaces, which is something I've been doing while a graduate student at the University of Wisconsin-Madison. My advisor is Dr. Matt Allen, who is currently at Brigham Young University, and this work was sponsored by Sandia National Labs and primarily supported by Dr. Dan Rotkin there. So in structural dynamics, the simplest way to represent some structure is in terms of its linear modal parameters, which are its natural frequencies, damping ratios, and mode shapes. With these, you can define a set of uncoupled single degree of freedom systems that superimpose to fully define the dynamic response of that structure. So in terms of an equation of motion, the natural frequency and damping ratio are constants that define the stiffness and energy dissipation of that mode. In structures that are weakly nonlinear, we can usually characterize their nonlinear behavior in terms of quasilinear modal parameters, which are simply amplitude-dependent extensions of the linear natural frequencies and damping ratios. Something that we usually denote as weakly nonlinear are structures with bolted joints. The material surfaces that are in contact about the bolt shift and slide when the structure moves, and that leads to nonlinear frictional effects that change how the structure responds. By allowing the modal parameter values to change with respect to the amplitude of the mode's response, we can approximate the variations that we observe in the stiffness and energy dissipation of the structure. So shown there on the on the right is the sort of behavior that we see with quasi-linear parameters typically, where the natural frequency decreases and damping ratio increases as the response amplitude increases. So now, in more complicated nonlinear systems, we can observe sorts of quasi-linear parameters that don't show a clear amplitude dependence to their respective modal amplitude, when several other modes are also excited, such that it appears as though the responses are coupled in some way, where the response of one mode has an effect on the behavior of another. And I believe this was something NASA ran into when testing the Orion crew vehicle, where they had issues parsing their experimental response data and correlating it to their FEM model due to some coupling that was coming up between modes of the structure. So now, as an extension of the quasi-linear modal parameters that I just mentioned, let's include the modal amplitude of other modes in with the amplitude dependence of the natural frequencies and damping ratio as a means of trying to include the effects of modal coupling between the modes. So now the issue with this is that it makes the system ID process much more difficult and convoluted, since now the nonlinear behavior of one mode basically depends on it's a function of all other modes of the structure instead of just its own mode. So, as a means of attempting to quantify and model the effects of modal coupling in an intuitive and digestible format, what I have to show here is basically a demonstration of how you can represent the coupling between two modes as a 3D surface, where the x and y axes are the modal amplitudes of two different modes, and the z-axis is the quasi-linear natural frequency or damping ratio of one of those modes. And then, so this should make it easier to visually see how much of an effect the modes have on one another, so how much they couple, and then also quantify that coupling at the same time. So now, basically, I'll just go right to an experimental demonstration, because there isn't really a numerical demo, because as far as I know, we don't really have a way of reliably modeling the sort of modal coupling we see experimentally yet. So hopefully what I show here is then a way of representing the effects of observed experimental coupling in a way that can be used to develop numerical models in the future. So the experimental structure that I'm looking at today, that I'm showing you, is the aptly named cylinder plate beam structure, or the CPB, which is a test structure at Sandia National Labs that they've used for quite a while in substructuring and nonlinear testing experiments. You can see in in the image there that it consists of a beam which is bolted to a circular plate, which is then bolted to a hollow cylinder. The interface between the plate and the cylinder is assumed to contribute most of the nonlinearity in the structural response due to all the friction that would occur between the surfaces. And at the back there, you can see that a shaker is attached to the end of the open end of the cylinder. And then this was used to excite the CPV with a variety of sine beats, or forced input. And then the response of that was measured by an array of accelerometers that are positioned across the beam, across the structure. And the linear mode shapes from a linear test were used to modal filter the responses down to a set, to modal filter the physical responses down to a set of modal responses. And in what I'm showing here, it's looking at the first three elastic modes of the system, which are basically the first cantilever modes of the beam and then a drum mode of the plate. So this is an example of the sort of forcing and response data that I have, which is, I used what is usually called a sine beat, where it's a windowed sinusoid. And what that does is it applies a very concentrated pulse of energy into a narrow frequency band. So you can use that to excite specific modes to a really high amplitude. Or if you superimpose two sine beats at different frequencies, you can excite two different frequency bands at the same time. So what I'm doing here is I'm applying isolated sine beats to each of the first three modes of the structure to excite them individually, and then to see what sort of quasilinear parameters they have when they're excited basically on their own. And then I'm superimposing sine beats to excite two different modes at the same time, and then just checking how do the identified quasilinear parameters change when other modes are also excited. And so the main so the other aspect of this is, so once the force dies down basically there, we have a sort of pseudo ring down within the response. And this data was taken several years ago for an initial attempt I had at trying to characterize modal coupling with the restoring force surface method. And then that didn't work out so well, so what I've been doing since then is basically trying to come up with a different way of looking at that data in a way that actually makes sense and works. And today what I'm presenting is part of that work. So now I'll show what I have for the isolated quasilinear parameters of each of the three modes, and then shown in the plots are the mode shapes from a FEM model of the cylinder plate beam, where the first mode is the soft direction cantilever, second mode is the stiff direction cantilever mode, and then the third mode is like a drum mode of the plate. So you could think of it, it's basically the beam moving in three different directions, three different perpendicular directions. So for the first mode, for each experiment, I have different force amplitudes. So what's here is a superposition. It's an overlay of a bunch of different tests done at different force amplitudes, and they overlay, so that's good, where it shows a consistency between the nonlinearity observed in each test. And then they sweep up in amplitude and then back down as it goes, because as it's going through the sine beat. It initially increases in amplitude and then rings out. So for each one, I have it. I'm using a method to identify the natural frequency and damping ratio called QLLSQ, where it's something I came up somewhat recently, and then I'll have a sort of appendix at the end of the presentation with more of an explanation of what that is, since it's relatively new. So the mode 1, the frequency basically traces out a pretty consistent backbone curve in the frequency, where it starts near the linear natural frequency of the mode and then softens with the increasing amplitude. And the damping has a consistent sort of bell shape where it initially increases and then decreases. And then mode 2 is a very similar behavior where it's a softening backbone and then this sort of bell-shaped damping with increase and then decrease. And mode 3 is also pretty similar when it's excited on its own, where it's a softening, stiffness, and then an increase and then slight decrease in damping. So that's the three modes on their own, which is it's very consistent nonlinear behavior. So now let's look at when we excite two of them. So excite them in pairs. So I have 1 with 2, 1 with 3, and 2 with 1, 2 with 3, and then 3 with 1, 3 with 2. So all the different combinations of these three modes. So first, an interesting one to look at is the mode 2 coupled with mode 1. So here the orange curves are where it's just mode 2, and then blue is when it's mode 1 and mode 2. So we can see that the frequency curves don't trace out the same sort of consistent backbone we have when it's just mode 2. And then the damping is sort of all over the place, where none of them really line up with each other. Yeah. So there's a shifting in the curves when mode 1 is also excited. So now if we rotate and change the perspective to be, if looking straight on from a mode 1 amplitude view, then we see that where before the blue curves were all spread out, now they basically line up, showing that these have a pretty good dependence on the mode 1 amplitude instead of mode 2. So now if we rotate the view again and then go to a more isometric 3D view, and then using these curves, using those points as a means of then just forming a surface from those by interpolating between the points as basically like a 3D point cloud, then you get something like this. And now if we rotate that, then it's easier to see. So now it's a surface where the curves follow along it, and it traces out a pretty consistent shape in a 3D space. So in this, what it looks like is the damping and frequency have this same sort of trend where they increase, like the frequency decreases no matter which mode is highly excited. So in the case where mode 1 is more excited, the mode 2 frequency is still softening. And then the same thing with the damping, where it has this increase and then sharp decrease. And it does that no matter if it's mode 2 is highly excited or if mode 1 is highly excited. So then that's basically the coupling between the modes, is that the mode 2 stiffness and damping is highly affected by the mode 1 amplitude as well as its own. And now this as mode 2 doesn't show that much coupling to mode 3, where now the frequency doesn't change that much at all, and the damping just changes a little bit. And now if we just jump to putting those as a surface, then that's what we see. Is it part of what the data that I have isn't as complete as it could. So this top sort of left corner here, there's not that much data defining what it is, and it's basically just extrapolating off of what I do have. But it seems like it isn't that coupled, where the biggest effect is this shift in damping as mode 3 gets highly excited. And now an interesting part is that it's sort of the opposite happens, with mode 3. So whereas mode 2, so mode 3 doesn't affect mode 2 that much, but the other modes affect mode 3 a lot. So here, the yellow curves are mode 3 on its own, and then blue is with mode 1 also excited here. And we see that there's this drastic shift in the frequency, and then also a big shift in the damping behavior. So this too, if we rotate these from the mode 3 to the mode 1 amplitude view, then the frequency lines basically all match up, and the damping behavior is still a bit wonky. And then if we put this into a surface and look at it, we see that this frequency behavior is really well defined, where it's a similar thing where if either mode 3 or mode 1 is highly excited, the frequency of mode 3 drops. And the damping has a sort of odd behavior, where the when mode 1 is highly excited, it's over on this sort of far side. But yeah, so that's the thing, is it's something that's hard to explain, but visualizing it like this makes it sort of just easier to see what's going on. And then this is mode 3 when mode 2 is also excited. It shows a similar behavior where the frequency is pretty heavily shifted and the damping as well. And it's a pretty similar plot to what you just saw. And then the last is mode 1 is just not that affected by mode 2 or mode 3. So it's a similar thing where the damping is slightly shifted down, but the frequency isn't that affected at all. And then mode 3 is a very similar outcome. So yeah, modal coupling is a very nonlinear structural behavior that's typically very difficult to model. And forced excitation can be used to, in the form of sine beats, can be used to selectively excite modes individually or in pairs at specific relative force levels, allowing you to control the degree of coupling that is activated and observable. And then the measured responses from that forced response, from the forced experiments, the measured response can be used to determine quasilinear natural frequency and damping ratio curves for each of the excited modes. And then by identifying the amplitude at each mode during that response, we can form a surface, we can construct a surface with respect to both amplitudes and the identified quasilinear parameters. And then visualizing these surfaces can help quantify the effect that modal coupling has on each mode, and then it also represents this single valued surface parameter that then effectively models the coupling as well. So then a future work is, I have an idea of augmenting the quasi-linear fitting process to just, instead of fitting each curve individually and then interpolating a surface between them, just to directly fit the surface in terms of 3D splines from the measured force and response data. And as a little addendum or appendix on how the quasi-linear modal parameters were formed or determined, it's a process that I came up with called QLLSQ, or quasi-linear least squares. So it's basically a variation, you could think of it as a variation of RFS, where instead of fitting the restoring force with response polynomials, you fit it with time polynomials. So it's setting up, assuming stiffness and damping aren't constant, you can represent them as an arbitrary polynomial. You can set up the equation of motion as a least squares solution for the coefficients of that stiffness and damping polynomial. And then from those you can back out what the stiffness and damping are. And then if you know what the amplitude is at each point in time, you can then back out the amplitude dependence. So yeah, that's what I have, and I look forward to hearing your questions. Stop the recording.